He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Hello and welcome to episode 54 of the Elemental podcast from RNZ. I'm Allan Blackman from the Auckland University of Technology.
And I'm Alison Ballance. And we're well on our way to visiting every element on the periodic table alphabetically. Today we're up to nitrogen, so let me see. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, number 7, atomic number 7, Alan.
Indeed it does. Nitrogen atomic number 7, elemental symbol N, and it was discovered in 1772. Next question, where did it get its name from? It comes from the Greek nitron and genes, and put those two together and that means niter forming. And then the question becomes, what is niter? And niter is the old name for a thing sometimes called saltpeter, or what we would now call potassium nitrate.
So as well as having the atomic number 7, she says, showing off her extensive chemical knowledge, I do know it's a gas.
Indeed it is, and it is all around us every day, every minute, every second of every day, because it makes up a lot of the air around us. And air was one of the obvious things that the early chemists studied. And so we've got some names here, people such as Sheila and Priestley and Cavendish. These were very, very famous early chemists of the 18th century. And they studied air, and what they showed that if you burned a candle in a limited supply of air, it would eventually go out, and the volume of the air that the candle was burning in would decrease by around about 20%.
So that's your oxygen?
Yeah, indeed. That's the reason. You've used up all the oxygen and you've got sort of 80% of the air left. And so they were intrigued by this, and so they went and put a mouse into this air after they burnt a candle in it, and of course the mouse would die.
Oi, cruelty to animals.
Yeah, a bit rough for the poor old mice, but obviously there was no oxygen in the air anymore. So in fact, the French word for nitrogen, which is azote, means without life, and that name was given by Lavoisier, another very famous early chemist of which some listeners may have heard. This name, without life, really is rather ironic for the very important fact that nitrogen is absolutely essential to life, and the majority of important biological molecules contain nitrogen. The nitrogen gas that makes up pretty much 80% of every breath that we take contains nitrogen molecules, and these are two nitrogen atoms bonded together by a triple bond. And triple bonds are very, very, very strong. And what that means is that the nitrogen gas in air is pretty much unreactive, okay? Now, that's a good thing and a bad thing. The reason it's a good thing is because the nitrogen in the air doesn't react with the oxygen in the air. And oxygen's a fairly reactive molecule. So, thankfully, nitrogen is so unreactive that the air remains air. But it's bad news for life on Earth, in fact, because nitrogen is so essential to life on Earth. So all living things need to be able to utilize the nitrogen in the air to build the molecules of life. And that is a little bit difficult when those nitrogen molecules in the air are held together by one of the strongest bonds in all of chemistry.
That's quite a claim to fame.
I know. It really is interesting. It's fascinating stuff, the chemistry of nitrogen. Let's quantify that last statement a little bit, all about strong bonds and everything. I could tell you that the nitrogen triple bond is around about 900 and something kilojoules per mole, but
exactly, and
probably wouldn't really mean a lot to you. Let's do this slightly differently. So let's take a mere 28 grams of nitrogen gas and assume that we can break all of the bonds in that nitrogen gas. If we could obtain all of the energy from all of those triple bonds in that 28 grams of nitrogen gas, you could boil around about 3 kilograms of water starting at room temperature.
Wow.
And you know how difficult it is to boil water. It takes a long time and a lot of energy to boil water. So there's a real literal truckload of energy in those nitrogen molecules.
It's pent up energy, eh?
Ha ha ha. So obviously, somehow nature can do this because living things are all around us and we're full of nitrogen as well. And nature can actually utilize the nitrogen in the air. It can break these bonds thanks to an enzyme called nitrogenase. And nitrogenase is found in microbes that live in the roots of legumes, beans and things like that. And these things can turn nitrogen into ammonia, and once we've formed ammonia, that can then be used by living things.
We talked about this with molybdenum, didn't we, a few episodes back? As it's also really important in the same process.
Yep, it's part of the enzyme. Yeah.
Go the mighty microbes for solving this chemical conundrum for us.
Indeed. It really does show you how good the microbes and enzymes are when you consider that humankind hasn't yet managed to duplicate this vital process as efficiently as nature can do it. So at the moment, the best that we can do pretty much is we can take nitrogen and hydrogen and mix them at high pressure and high temperature, and we can get ammonia out of that if we throw in a catalyst with some iron in it. And this process has been known for over a century now. It's called the Haber process, and this is after a guy by the name of Fritz Haber, who was the winner of the Nobel Prize for Chemistry in 1918, precisely for this process. And that's kind of ironic. Okay, 1918, remember we had sort of a world war going at that stage. And it could be argued, if you look at it, that the Haber process actually lengthened World War One. Okay?
How come?
Well, the reason being, in order to make gunpowder, you need a thing called saltpeter. We talked about this earlier. So you need nitrates to make gunpowder. Now, Germany got all of its nitrates from Chile, but as soon as World War I started, the British blockaded Germany, and so they couldn't get access to these nitrates. They needed an alternative source of these. And so they turned to the Haber process and they said, oh, here we go. We've got lots of ammonia here. We can turn ammonia into nitrate and then we can use that in gunpowder. So kind of ironic he got the Nobel Prize for, potentially lengthening World War I, but that's just my opinion. Revisionism, I think they call it, don't they? So Haber was also, unfortunately, involved in the first use of poison gas, which I think we've talked about on the previous episode relating to chlorine.
We did talk about that a very long time ago.
We did. And as a result of this, rather tragically, his wife, who was obviously a woman of high moral standing, went and shot herself with his gun, unfortunately.
She didn't like what he'd done.
No, indeed. Very,
Not
very
surprising.
tragic. So why ammonia? Why is ammonia so important? Well, it's used as a fertilizer. It's used to make fertilizers. And this Haber process is such an important process for life on Earth that, get this, it consumes an estimated 1 to 2% of all of the energy generated on Earth annually. And
Wow.
that is a statistic that never fails to amaze me. And obviously, if some bright spark chemist out there can figure out a way of carrying out the Haber process at room temperature and atmospheric pressure, they are A, going to make themselves a hell of a lot of money, B, win a Nobel Prize, and C, save the planet.
Now, if it takes lots of energy to break the bonds in nitrogen, like you were saying, is the converse true?
It is absolutely true, as anybody who's ever studied first-year thermodynamics would know.
Oh, the first law of thermodynamics, heat always moves from the hotter to the colder. Is that
Indeed.
something like that?
You've been listening to Flanders and Swan,
That is
I
a
think.
Flanders and Swan
Yes.
attribution, that one. Thank you.
Yeah, as we said, if you've got to put a lot of energy in to break these nitrogen triple bonds, then if you can actually make these nitrogen-nitrogen triple bonds, you are going to release an awful lot of energy. And because of this, what we find is that nitrogen compounds, or compounds containing nitrogen, shall we say, are very, very often found in explosives, of all things. So things like ammonium nitrate, nitroglycerine, TNT, Semtex, and C4 contain molecules that are all high in nitrogen. And the reason that they explode is that the nitrogen atoms that are in all of those compounds would much rather be in a nitrogen molecule. And so they get together, form this triple bond, give out a huge amount of energy, and also occupy a much greater volume, because we're talking about a solid going straight away to a gas.
That link that ammonia can go one direction and be a fertiliser, and in another direction it becomes an explosive. I know that's got friends of mine into trouble at airports where they do that swabbing for explosives. And, it picks up the fertiliser that they've been putting around the garden rather than the explosives that they don't actually have in their luggage.
Yeah, things like ammonium nitrate and stuff you can use as fertiliser, and sadly people have in the past. They've made these bombs just out of fertilisers. But that is the way that nitrogen works. We've talked about nitrogen in the air, so that's the gaseous form. You can liquefy nitrogen if you cool it down to negative 196 degrees Celsius, and that is used extensively, in fact, as a coolant, because negative 196 degrees Celsius is, in fact, not too cold to cool things down to, believe it or not. What do we use liquid nitrogen for? Well, rumour has it that Walt Disney may well be immersed in some.
So he's been cryopreserved.
Well, rumour has it, indeed. Far be it from me to spread rumours, but...
Well, I can't speak for Walt Disney, but I have done stories in the past about cryopreservation of sperm from rare birds.
And that does work. That absolutely does work. We can vouch for that one. And also with the liquid nitrogen thing, if you've ever been to the doctor and had a wart burnt off, quote unquote, that would have been liquid nitrogen that was being used in that.
Interesting fact, please, Professor.
Okay, here are two.
Oh, hurrah.
If you've got an organic compound, and we've talked about organic compounds before, they're made predominantly of carbon and hydrogen. But if you've got an organic compound that's got one or more nitrogen atoms in it, what we call them is amines. That's the technical term. And so the word vitamin comes from the combination of the words vital amine. Okay, put them together, shorten it, you get vitamin. And again, this is rather ironic because some vitamins, so for example, vitamins A, C, D, and K, don't actually contain nitrogen, so they're not amines at all.
And it proves that we should definitely call them vitamins, not vitamins.
Yes, please. Thank you.
You're welcome, Mr. Pedantic.
And another interesting fact is that nitrogen is, as we said, often used in explosives, but in this case, it's a life-saving explosive. And this is a compound called sodium azide, and that has the formula NaN3. And the reason it saves lives is because it is the explosive that is used in airbags. And so what happens here, your car crashes, so we get a whole lot of little sensors, and that inflates the airbag by getting the azide ion to react very, very rapidly, and again change from its solid form to nitrogen gas. Huge increase in volume there, inflates the airbag, saves your life.
Really? Another life-creating and life-saving chemical element in so many ways. Thanks, nitrogen. This has been episode 54 of Elemental. You can find us at rnz.co.nz/chemistry.
And we're also a podcast, and you can subscribe for free at your favourite podcast provider. We'll catch up with you next time for Osmium. But until then, I'm Allan Blackman.
And I'm Alison Ballance. Mā te wā.